Welcome to the data layer of IT 7014. If you want to see what a systemic meltdown looks like, look closely at a monolithic database forced to do everything at once. Massive energy waste at scale rarely comes from stray coding errors. It comes from architectural mismatches. When a system performs complex, unnecessary computations just to organize information, it drains power for zero user benefit. To fix this, we have to look at the geometry of the information itself. We must map the specific shape of our data to the correct database engine. Second, we must stop user requests from ever reaching that database in the first place by deploying precise interception layers, otherwise known as caches. In this session, we will define the three core database types, master the concept of polyglot persistence, trace caching paths, and dismantle specific traps from the Quiz 9 and 10 exams.
All data as if it behaves exactly the same is the fastest way to throttle a system and destroy its sustainability metrics. Form dictates function in database selection. Before choosing a storage mechanism, you have to determine how the data naturally groups together. Look at this architectural breakdown, starting with the relational column. Think of this as a highly disciplined spreadsheet. It organizes information into strict tables with distinct rows and columns. Use this structure when your application demands clear relationships between entities and requires multi-record transactions, like a banking ledger where correctness takes priority over raw speed. Moving to the document column, we find a much more flexible structure. Picture a thick physical file folder. Each record is a self-contained JSON document that can hold nested fields and lists. Because everything required is already packed into that single document, retrieving it requires no complex joins. This is exactly what you need for product catalogs or user profiles. Finally, examine the time series column. This operates like an unalterable logbook. It is optimized for an endless stream of time-stamped data points that are almost always appended in order and rarely updated. For tracking sensor readings or application metrics, this structure executes time range queries with incredible efficiency. If you force one of these data shapes into the wrong engine, you force the database to perform constant structural conversions. It builds excessive indexes or scans large amounts of irrelevant data. Correctly matching the data shape to the storage engine eliminates this internal friction, which translates directly to lower energy consumption per request. Let's see what happens when we ignore these shapes. Imagine 200 million sensor readings arriving every hour, slamming into a rigid, general-purpose relational database. The database is forced to maintain complex transaction logs and update heavy B-tree indexes for every single insertion. The sensor data requires absolutely none of these features, resulting in massive wasted CPU cycles. The solution is an architectural pattern known as polyglot persistence. Instead of routing every workload through a single bottleneck, we deploy multiple database types within the same system, allowing the traffic to flow to the engine built specifically for its shape. In a large retail platform, this means keeping customer financial accounts in a strict relational database, housing the detailed product catalog in a document database, and sending the real-time operational metrics straight to a time series database. Managing three distinct database engines introduces significant operational complexity for the engineering team.
Accepting that upfront complexity is the only way to avoid compounding computation waste at enterprise scale. Even with the perfect database engine, the most efficient query is the one that never happens. We protect the origin database using caching, an interception layer that stops requests in their tracks. This diagram illustrates where these caches sit in the request path. A single request might be stopped locally by the user browser, out at the edge by a content delivery network, deeper inside the application cache, or finally at the database query cache. Notice the red arrow mapping the energy and latency costs. Every layer that satisfies a request prevents energy from being spent in the layers behind it. A file caught by the browser avoids network transmission entirely. When a request finds its target in the interception layer, it is a cache hit. When it fails and continues onward, it is a cache miss. The energy benefits scale linearly with that hit rate. If a CDN operates at a 95% hit rate, the origin servers only process 5% of the total traffic, drastically reducing the required server footprint. Caching is an architectural necessity. It is the primary mechanism for dropping the energy cost of repeated computations to near zero. Let's apply these concepts directly to the upcoming Quiz 9 and 10 exams. We need to dismantle a few common testing traps. Question 2 asks you to categorize a customer order that is created once, read as a single unit, and includes a creation timestamp. The trap is right there in the word timestamp. Students see it and immediately jump to time series. Look at the actual shape of the data. The order contains a shipping address and multiple line items packed together. Because it has nested fields read as a whole object, it strictly belongs in a document database. Question 4 presents a scenario where a cache is added to an application, but the database load barely drops. The trap distractor suggests the database is simply faster than the cache. The reality is mathematical. If the database load didn't drop, the cache hit rate was too low. Most requests missed the cache entirely and fell right through to the database, continuing to consume processing power. Finally, Question 14 describes an application choking because it is feeding millions of sensor readings into a relational database. The test will try to trick you into selecting sample the data or move everything to a document database. Neither solves the architectural failure. The correct action is to implement polyglot persistence, extracting the sensor data and routing it directly to a time series store. These exam traps prey on legacy, one database fits all thinking. Achieving high scores and building sustainable systems requires you to match the shape to the store. We have identified the distinct shapes of data, applied polyglot persistence to separate them, and mapped out caching layers to intercept redundant queries. But placing a cache is only the beginning. The next level of architectural complexity arrives when the underlying data changes, threatening to serve stale information to your users. In Part 2, we will evaluate the exact energy costs of write-through versus write-back strategies, time-to-live expirations, read replicas, and connection pooling. Be prepared. These upcoming topics feature Professor Faustino's favorite swap pair exam traps. Study the shapes, check your hit rates, and keep your architecture sustainable. We'll see you in Part 2.